Bismillahirrahmanirrahim. Assalamu alaikum students. Welcome to our 17th lecture of MTH108 Business Math 1. Today we will continue with our chapter 7, which is about exponential and logarithmic functions. Let us revise what we have done in our last lecture. In our last lecture we have studied the properties of exponents and radicals. Then we have studied the definition of exponential functions and the special cases of exponential functions. What do we mean by the special cases or special classes of exponential functions? That is, exponential functions of the form y is equals to a b to the power mx, where a is equals to m is equals to 1. And this other class was when b was the irrational number e. Then we have studied the cases of exponential functions, that is when the value of b is strictly 0 and 1, and the second case when the value of b is strictly greater than 1. In our last lecture we have also seen the graphs of exponential functions and the translations of the exponential functions. With the help of the graphs and the translations, we have characterized our exponential functions particularly about the domain, range, the x-intercept, y-intercept, and so about the increasing function or decreasing function. In the end of our last lecture, we have studied that how we can convert any base to the natural base e. Okay. So, what we will study today? Today we will study about logarithms. We will see some properties of logarithms. You have already solved these examples, solved these properties of logarithms in your college classes, but today we will see them in detail. We will also, with the help of these properties, we will also solve the exponential equations and the logarithmic equations. After this we will graph the logarithmic functions as we have done with the case of exponential functions, and we will see some characteristics of logarithmic functions. And in the end of today's lecture we will see some word problems or some applications of log functions in daily life. Okay, we start with our today's lecture. First we define what do we mean by a logarithm. A logarithm is the power x to which a base b must be raised in order to yield a given number y. That is, y is equals to b to the power x. So the logarithm is the power x, this power, to which a base b must be raised, that is b must be raised to some power x in order to yield a given number y, that is our left hand side, this number y. Okay. Now this definition may not be clear to you at first sight, but what do we mean by this logarithm is the power x to which a base b must be raised? So it is basically the power of some base b, that is we raised our base to some particular power to obtain a particular number y. Since we are saying that logarithm is a power, which means that logarithm is nothing but an exponent. For example, if we consider the equation 2 cube is equals to 8, this is an exponential equation. Okay. Now here 3 is the exponent, which can be considered as the logarithm to the base 2 of the number 8. That is what we are doing if we compare our equation 2 cube is equals to 8 with our definition, that 3 is the power or the exponent which is raised to the base 2 to obtain a given number y, which is equals to 8 here. Or what do we mean by this? That we are saying that this 3, this exponent is the log, that is 3, this exponent is the log of the base 2 to obtain a given number y, which is equals to 8. Okay. Now, using this definition and example, we give the general definition of what do we mean by the logarithm. So, in general, we are saying that if y is equals to b to the power x, this is nothing but equivalent to, now y is equals to b to the power x is our exponential equation, and we are saying that x, this exponent x is the logarithm, this exponent x is the logarithm to which the base b is raised, to obtain some particular value y, where the base b should be greater than 0. So, if we have an exponential function y is equals to b to the power x, then logarithm is nothing but the exponent x, which is equals to the log of the base b to obtain the particular number y. And we have a condition here on the base that the base b should be positive, strictly greater than 0. Okay. We are restricting ourselves to the base b of positive values, and the second condition is that the positive values other than 1, that is, the base should be different from 1. So, with the help of this general formula, that whenever y is equals to b to the power x holds, that is, whenever this exponential equation holds or there exists an exponential function, for that exponential function there always exists a logarithmic function, that is, x the power or the exponent is equals to log to the base b of the number y. So, we have seen that logarithmic functions are related to exponential functions. What do we mean by this? Suppose we consider an exponential function y is equals to 2 to the power x, where b is the base 2 positive greater than 0 and b is definitely different from 1. And in our general form, we are saying that the exponential function is related to the log function. Consider a particular form of exponential function y is equals to 2 to the power x. Then what will be the graph of this exponential function? We have studied the graphs of exponential functions in our previous lecture. The graph will approximately look like this, because b is greater than 1, so the graph will be an increasing function rising from left to right. Y is equals to 2 to the power x, which means that if x is equals to 1, then y is equals to 2. Okay, or if x is equals to 2, then y is equals to 4. So, for x is equals to 2, y is equals to 4. Here the function f is sending an input x to the output y. That is, here the function f or the rule f is assigning 2 is assigning the values of 2 to the output y is equals to 4. Okay. That is, f sends an input x to the output y. When the input is 2, the output is y, which is equals to 4. And the output is always positive. If we recall from our previous lecture that we have seen that the range of exponential functions is always the positive real line, that is, the graph always lie above the x-axis. So, f is sending any real number x to some positive number y. Okay, let's consider this graph again. y is equals to, consider this graph again, y is equals to 2 to the power x. For the value of x, y is 2. For the value of 2, let's say this is 2 and this is 4. Okay. Now, that is from the y-axis to the x-axis, what is happening? The output, corresponding to the output y is equals to 4, there is only 1 and 1 input, x is equals to 2. So what is happening, that for each output y there exists only one input x. What are we trying to say? That with each positive value of y, we can associate exactly one value of x. That is what is happening if we shift our graph and we consider the y as the set of inputs and x as the set of outputs. Then with each positive value of y, we are associating only one value of our output x, which means that our first graph is the graph of exponential function and the second graph is the graph of our log function. That is, exponential function is giving for the input x is equals to 2, the output 4, and the log function is bringing that output back to 2. So what do we mean by this? That bringing that output back to 2, we say that the log function is basically the reverse action of the corresponding exponential function. That is, our exponential function is shifting 2 to 4 and the log function is shifting back 4 to the same value 2 from where we have started. So log function is nothing but the reverse action of the corresponding exponential function. And then we say that the logarithm function is the inverse of the exponential function and vice versa. That is, log function and the exponential function are nothing but the inverses of each other. Okay, let's have a look at some examples where we'll have first the exponential equations and we will transform these equations into the corresponding log equations. Okay, for example, if we have our exponential equation 2 to the power 4 is equals to 16, then the equivalent logarithmic equation will be equals to, here we have base b is equals to 2, exponent x is equals to 4, which means that writing this exponential equation in the logarithmic form is nothing but we will use our this general form. I write it here again. That is, whenever we have our exponential function y is equals to b to the power x, this is nothing but that the exponent is the log with base b of that particular number y, with the conditions on b that b is greater than 0 and b different from 1. So we are given with an exponential equation, and with the help of this general formula we can write the equivalent logarithmic equation of this exponential equation as, this is nothing but 4 is equals to log with the base b is equals to 2 of 16. Okay, one more example. If we have our exponential equation as 10 square is equals to 100, then we can write this exponential equation in the log form as 2 is equals to log to the base 10 of 100. Okay, our exponential equation is 3 cube is equals to 27, and the corresponding logarithmic equation will be equals to 3 is equals to log of 27 to the base b is equals to 3. One more example, we have 10 to the power minus 1 is equals to 0.1, and the corresponding logarithmic equation will be equals to minus 1 is equals to log of 0.1 to the base 10. Since we have said that the base b should be strictly greater than 0, so here we can see that log of base 10 or log of base 3 or log of base 2 are all defined values. And the values of y are all positive reals. However, the value of x in our exponential function is the set of all real numbers. So our domain is the set of all real numbers. So in our example 4, the exponent of 10, which is equals to minus 1, is allowed. There is no harm in taking the negative exponents, because we have studied in our previous lecture that by using the property of exponents, we can replace every negative exponent by a positive exponent by just taking its reciprocal. So in these 4 examples, we were given with the exponential equations, and with the help of our general formula, we have rewritten these exponential equations in the corresponding log equations. Now we do the other way round, that is, now we will be given with few logarithmic equations, and again using this general formula we will write our log equations into the corresponding exponential equations. We have our log equation as 4 is equals to log of 10,000 to the base 10, and this is nothing but, okay, for the sake of memorizing and simplicity, I write the general formula here again, where the general formula is y is equals to b to the power x is the exponential form, and this is equals to x is equals to log of y to the base b, where the base should be positive and different from 1. Okay, now we have our log equation, and we have to rewrite this equation in the exponential equation. We have to identify first what is b, what is y, and what is x. X is clearly 4 here, the base b is equals to 10, and y is equals to 10,000. So the corresponding exponential equation will be equals to y is equals to b to the power x, and if we solve this equation we obtain the left hand side, which is 10,000. Okay, now one more equation, 3 is equals to log of 64 to the base 4. This is equals to 4 cube b to the power x is equals to 64. Okay, one more example, we have 2 is equals to log of 25 to the base 5, and the corresponding exponential equation will be equals to 5 square is equals to 25. Okay, now we have one more equation, minus 2. Minus 2 is the value of x, because we are writing our log equation, log of 0.01 to the base 10. So if we compare this log equation with the general form, we obtain that x is equals to minus 2, y is equals to 0.01, and the base b is equals to 10. And since we have our domain x as the set of all real numbers, so minus 2 is also acceptable. And simplifying or writing it in the exponential form, we write it as base b, which is 10 to the power minus 2, which is equals to 0.01, where 10 to the power minus 2 is nothing but 1 over 10 square, because here we have a negative exponent, and we can replace this negative exponent by the positive one just by taking its reciprocal, which is further simplifying equals to 1 over 100, and which is equals to 0.01. Okay, now one more example. If we have x is equals to 1 by 2, written as the log of 8 to the base 64, then the corresponding exponential equation will be equals to 64 to the power 1 by 2, which is under root 64, which is equals to 8 according to the general formula. So now we have seen some examples in which if we are given either the exponential function, we can convert it into the corresponding log equation by using the general form, and vice versa. Okay, here if we look at our examples, we have seen that the base b can take any positive value other than 1. In the first example, the base was 10. In the second example, the base was 4. In the third one, it was 5. Fourth one, it was 10 again. And in the fifth one, it was 64. Okay, now we look at the notation of our log and the common bases which we use in our daily life. There are two most commonly used bases for logarithms, that is the base 10, that is when b is equals to 10, and base e, that is when b is equals to our irrational number e. And the base 10 logarithms are known as common logarithms, and the base e logarithms are known as natural logarithms. Common logarithms are denoted by x is equals to log of y to the base 10. b is equals to 10 here. Or more generally as, since if we know that in which base we are working or which base we are using, if we know that throughout we are working with base b is equals to 10, or we are working with the common logarithms, then we do not write the base 10. We simply write it as x is equals to log of y, where from this equation or this form it is understood that we are considering the base b is equals to 10. Okay, we have some similar notation for the natural logarithms, that is the natural logarithms are denoted as x is equals to ln natural log of y to the base e. And once we are sure or we know which base we are working, or we are working only with the natural logs, then we only write it as x is equals to ln of y, where from this form it is clear that throughout we are working with the natural log only, or the logarithms with the base e only. If we have a logarithm having a base b other than 10 or e, then we write it as x is equals to log of y to the base b. Generally we write as, if we don't know which base we are using, or if we are using some base other than 10 or e, then we write it as x is equals to log of y to the base b. Now we come to some properties of our logarithmic functions. Why do we need these properties? Because in case of computations of very large or very small numbers, the use of properties increases the efficiency of solving the problem. That is, by using these properties, we make our computations very less and very quickly and easily. The first property, which we all know and we have used it many times, is if we have two numbers u and v, then the log of u and v to the base b is equals to log of u to the base b plus log of v to the base b. What we are trying to say in this property is that log of the product, that is, we are taking the log of the product u and v, is same as sum of the respective logs. That is, log of the product is same as sum of the respective logs, that is log of u and log of v. For example, if we have our number 100 into 1000 to the base 10, and we are asked to solve this product with the help of log to the base 10, then we will simply use our log property, that since inside we have a product, we will take the separate logs and add them. That is log of 100 to the base 10 plus log of 1000 to the base 10. Okay, if we are asked to find the natural log we represent by ln, and the common log we write as log. If we want to find the natural log of 80, that is, it is the natural log or log of 80 to the base e, then we can simply split this 80 into two products, as we can write it as log of 40 or log of 4 into 20, and now we have a product of two numbers inside a log, so we will take the separate logs and add them. We obtain log of 4 plus log of 20. Okay. Now our second property. This property we have also used many times, that is log of some number u with the exponent n to the base b is same as the exponent n times the log of u to the base b. That is, log of the exponent is power times the log of the number. For example, if we have log of 100 square to the base 10, then the power, the exponent will come as the multiple, that is, it will be equals to 2 times log of 100 to the base 10. We can also use we can verify our result by using our first property. How? Okay, now we have log with the base 10, and 100 square means 100 into 100. So we are taking the product of the log with the same base. Using our property 1, we obtain that this is equals to log of 100 to the base 10 plus log of 100 to the base 10. And then adding these two things, we come back to our same result, that if we have a log of exponent, then it becomes the power, then the power becomes the multiple of the log, which is equals to 2 times log of 100 to the base 10. For example, we want to find the natural log of 8, then instead of remembering the table or using the calculator, we can simply solve as if we know the values of the basic logs. This is equals to log of, we know that 8 is equals to 2 cube, and now we have something in the exponent form, in the power form. So the power will become the multiple, that is, it will be 3 times natural log of 2. And if we know the value of natural log of 2, we can easily find the value of natural log of 8. Now we will come to our third property of log of the ratio, that is, if we have two numbers u and v in the ratio form, that is u over v, and we want to take their log with some base b, then log of the ratio is same as difference of the logs, that is log of u to the base b minus log of v to the base b. Log of ratio, left hand side is saying us that the log of the ratio is equals to the difference of the log. Okay, for example, if we have log of 8 over 5 to the base 10, now we have log of ratio, then we will take the difference of the logs, that is the log of 8 to the base 10 minus log of the denominator, which is 5 to the base 10. Okay, if we want to find the natural log of 3.5, then we know that 3.5 is equals to 7 by 2, and now we have log of ratio, so it will be the difference of log of numerator minus log of denominator, and the value can be negative. If we obtain some answer as a negative number, then there is nothing to worry about. Okay. Now we come to our fourth property, that log of b with the same base b is equals to 1, which means that log of any number with the same base is always equals to 1. For example, log of 10 to the base 10 will be equals to 1. Natural log of e, and natural log means log to the base e, will be always equals to 1. We can verify this result by using the general form or the equivalent form of the exponential function. That is, we have log of b to the base b is equals to 1. So this is our x. Okay, the base b remains the same, and this b is equals to y. We obtain that b to the power x is equals to y, and x is equals to 1 here. This implies that b to the power 1, which is b, again by using the property of exponents, that any exponent raised to power 1 is the same exponent, and the right hand side y is b. So this verifies that log of any number with the same base is always equals to 1. There's one more interesting property, and which we use it many times, that log of the number 1 with any base is always equals to 0. For example, log of 1 to the base 10 is 0. Natural log of 1 to the base e is 0. If we want to verify this result by using the equivalent exponent form, what do we obtain? We obtain that 0 is the x here. We obtain that b to the power 0 is equals to 1, and which is true by using the property of exponents. That is, any number raised to the power 0 is always equals to 1. So property 5 says that log of 1 with any base is always equals to 0. Now we come to our sixth property, which says that b to the power log of x to the base b is equals to x. And we can verify this result by using the equivalent exponential form. For example, if we have 10 with the exponent as log of 100 to the base 10, then we will obtain the answer 100. So if we have some number with the exponent as the log of the same base, some number b with the exponent with the power as log of the same base b, then we are left with only the number x. Or we can simplify the right hand side as 10 by using the property of logs. We know that 100 is nothing but 10 square to the base 10, which is equals to, now the exponent will come as the multiple, which we obtain 10 to the power 2 times log of 10 to the base 10. And we have just studied the property that the log of a number with the same base is equals to 1. So we obtain 10 square into 1, which is equals to 10 square, which is 100. Seventh property says that if we have log of some number b to the power x, log of the exponent with the same base is equals to x. For example, log of 2 to the power 5 with the same base 2 is nothing but 5. And again we can use our property in this case that log of 2 to the power 5 with the base 2 is equals to, here 5 is the exponent, this will come as the multiple. So we obtain 5 times log of 2 to the base 2, and any number, log of any number with the same base is 1. So we obtain 5 into 1, which is equals to 5. One more example of the same property. If we have natural log of e cube, then we should obtain the answer 3 only. Why? Because from this property and by using the property of exponent shifting as the multiple, we obtain the left hand side as 3 times log of e. Now we have natural log of e to the same base e, which is equals to 1, and we are left with 3 only. Now if we have log of the ratio 1 over v to the base b, then this is nothing but minus times log of the number with the same base b. We can verify our right hand side by using the property of exponents, that is log of 1 over v is same as v to the power minus 1, which we have seen in our last lecture. And now minus 1 is the exponent, so exponent will come as the product, that is minus 1 times log of v to the base b, which is our right hand side. Or to verify this, we can also use our property of log of the ratios, that is log of the ratio 1 over v is same as log of 1 to the base b minus log of v to the base p. We have just seen in our previous properties that log of 1 to any base is 0, so we obtain 0 minus log of v to the base b, and we obtain our right hand side. For example, if we want to find the log of 2 by 3, then this is nothing but minus times log of the reciprocal, which is 3 by 2. Okay. Now our ninth property says that if we have a number u and we want to take the log of this number u to the base b, but in actual we want to find the log of u to some other base different from b, then how we change the base? We take the log of u to the new base a, our required base, divided by log of the base b to the new base a. For example, if we want to write our log of x as natural log, so how we will change our base? Our log of x is nothing but log of x to the base 10, and we are interested in writing this x in base e. How we will write it? We will use our rule, that is log of x to the new base e divided by log of the base, which is 10, to the new base e, and simplifying we obtain in the numerator as log of x divided by natural log of 10. So given any base b, we can convert this base or write our log in some new base by using this ratio formula. For example, if we are given the log of 5 to the base 2 and we want to convert this base b is equals to 2 to the base b is equals to e, how we will write it? This is nothing but log of 5 to the new base e divided by log of 2 to the new base e, which is, upon simplifying, we obtain natural log of 5 over natural log of 2. So now we have seen some properties of logarithmic functions. Few of them were new to us, but most of the properties we have used them many times, and now we have seen them with examples in details. Now we will use these properties to solve our logarithmic equations. Up to now in our previous chapters we have only solved the polynomial equations, particularly our linear equation, quadratic equation and cubic equations. Now we want to see that if we are given some exponential equation or logarithmic equation, how we will use these properties to solve that particular equation. For example, we are given a logarithmic equation log of x square plus log of x is equals to 9, and we are asked to solve this equation. First we will use some properties. If we look at our first term, which is log of x square, we can see that we can use the property of exponents, that is log of x square will be equals to 2 times log of x plus second term as it is log of x is equals to 9. We can simplify our left hand side and we obtain 3 log of x is equals to 9. Dividing both sides by 3, we obtain natural log of x is equals to 3. Or we obtain x is equals to e cube, which is equals to which is equals to 20.085. So if we are given a logarithmic equation, we can solve this logarithmic equation very easily by using the properties of log and the properties of exponents. What we have done in this example is simply we have used the property of exponents, that the exponent or power will be the multiple of the log. So we obtain 2 log of x plus log of x is equals to 9. Simplifying, we obtain 3 log of x on the left hand side and 9 as it is. Dividing both sides by 3, because 3 is a non-zero number, division is possible. Log of x will be equals to 3. And what do we obtain? We obtain x is equals to e cube, which is equals to 20.085. We will see that how we have obtained x is equals to e cube simply by taking the exponential on both sides. We have taken the exponential on both sides. On the left side we are left with x, and on the right hand side we are left with e cube, and e cube is a constant which is approximately equals to 20.085. Now second example, we have log of x square plus 2 is equals log of x square plus 2 minus, there is no equal here, minus log of x square is equals to 2. Okay, we have to solve this log equation. Again, if we look carefully on the second term, we can write log of x square as 2 times log of x square. So we obtain log of x square plus 2 minus 2 log of x is equals to 2. Now we have log of a minus log of b with the same base. We can combine both the log terms by log of x square plus 2 divided by, okay, now we will use our property 6, that is taking exponential on both sides. We obtain e to the power log of x square plus 2 divided by x square is equals to e square. Now the log and exponential will cancel out, and on the left hand side we are left with x square plus 2 divided by x square is equals to e square. Now we have a quadratic equation in x square, and we can easily simplify it or find the roots of the x, where we know that e square is equals to 7.3891. Okay, so right hand side is equals to 7.3891 x square. Okay, simplifying, we obtain that 2 is equals to 6.3891 x square by taking the x square on the right hand side, and now dividing 2 by 6.3891, we obtain x square is equals to 2 over 6.3891, which is equals to 0.313, and by taking the square root on both sides, we obtain the possible values of x are plus minus 0.5595. So just by using our properties, we can easily simplify our logarithmic equation and find the value of x satisfying the equation. E to the power 2x is equals to 5. Then how we can solve this exponential equation? By using our properties to find the value of x. Okay, we will use our property 7 here. Property 7 says that we will take the log on both sides, that is the natural log of e to the power 2x is equals to natural log of 5, and the natural log and base and the number are same, so it will cancel out, and we will obtain 2x is equals to natural log of 5, and x is equals to natural log of 5 divided by 2, which is equals to 0.8047. One more example. We are given with log of x minus 1, log of x plus 1 minus natural log of x is equals to 0.5, okay, which is equals to 1 by 2. Now here we have one term as log of x plus 1. Can we write it as natural log of x plus natural log of 1? No, this is not correct. We will use the ratio property and simplify the left hand side as log of natural log of x plus 1 divided by x is equals to 1 by 2, and by using our property 6 again, that is raising it to the same base, which is e here, that is exponential to the power log of x plus 1 divided by x is equals to e to the power 1 by 2, which is equals to under root e. Exponential cancels out with log, and we are left with x plus 1 over x is equals to under root e. Now this is a linear equation in one variable x, and we can simply solve it by writing as x plus 1 is equals to x under root e, or under root e minus 1 into x is equals to 1, or x is equals to 1 over under root e minus 1, which is equals to 1.541. By simplifying and using the values from the calculators, we can write it as 1.541. So now we have seen some equations containing the logs and the exponentials, which we can solve easily by using the properties of exponents and the logarithmic functions. That first we will simplify our log terms or the exponential terms, then we will take the log or the exponential of the same base and solve for the unknown variable x. Now in solving these exponential or logarithmic equations, most of the students make many mistakes. For example, one mistake which I have pointed out here as they will simply open natural log of x plus 1 as natural log of x plus natural log of 1, which is not true. So let's look at the common mistakes which we do most of the time. For example, if we have log of the sum m plus n to the base b, then sometimes we write it as the sum of the logs, that is log of m to the base b plus log of n to the base b. Okay, if we ignore this inequality sign in between, what do we see? That the left hand side is saying log of the sum and the right hand side is saying sum of the logs. This property does not hold for logs. So log of the sum is never equals to sum of the logs. For example, the same thing which we have seen in our example, that is natural log of x plus 1 is never equals to natural log of x plus natural log of 1. Second most common mistake, we do the same thing when we are subtracting, when we are taking the log of the difference, we write it as log of m minus log of n. That is, we write as log of the difference as difference of the log, and this is always not equal. For example, natural log of, let's say, x minus 1 is never equals to natural log of x minus, or we may write here as log, minus log of 1. Okay. Third common mistake is something to do with the ratio. If we have two logs in the ratio form, that is log of m to the base b to log of n to the same base, we simply write it as log of m minus n to the same base, and they are in general never equal to each other. That is, log of the ratio is not equals to log of the difference. For example, log of x square minus 3 can never be equals to log of x square divided by log of 3. Now the last common mistake which we do most of the time is again with the ratio, that we have log of m to the base b with the ratio of log of n with the same base b, and we write it as the common log of the ratio m over n to the same base, and they are never equal. For example, log of x square by 3 is never equals to log of x square divided by log of 3. So in solving the logarithmic and exponential equations, we really have to take care that we use the correct property and not the wrong one. If we are using the wrong property, then in fact we are complicating the given equation and we are not solving for the unknown x. Now we come to our next topic, which is about the graphs of logarithmic functions. In our last lecture we have seen the graphs of exponential functions and about the properties or the characteristics of the exponential functions with the help of graph. In this lecture we will sketch the graphs of logarithmic functions, and with the help of graphs we will generalize their characteristics. Now we know that when an unknown variable is expressed in terms of the logarithm of another variable, then such a function is known as a logarithmic function. That is, a logarithmic function with base b has the form y is equals to f of x, which is equals to log of some unknown to the base b with some conditions on the base b, as b, the base should be positive and the base should be different from 1, and the function of which we are taking the log should be strictly positive, cannot be equals to 0. For example, if our function f of x is log of x to the base 10, or natural log of x to the base e, or our function f of x is log of x minus 1, or our function g of x is log of x square minus 2x plus 1, then these are all the log functions of some unknown x or of some unknown function which is allowed only to take the positive values, where the unknown function is x, x minus 1, x square minus 2x plus 1, and so on. It can be any function with the condition that the function should take only the positive values greater than 0. First we sketch the graph of our logarithmic function with the base 10, that is the graph of common logarithm. We consider the function y is equals to log of x to the base 10. Then to find the graph of this function y, how we will find the graph of this function, or how we will graph this function? We put the values of x, the independent variable, and calculate the corresponding values of the log function, which gives us the output y. But this method is not so easy to calculate the ordered pairs x and the corresponding values of the outputs y. So in order to sketch the graph of this log function to the base 10, what we do, we simply convert this log function into the corresponding exponential function, which is nothing but 10 to the power y is equals to x. So now with the help of the values of y and x, we can easily generate the graph of this logarithmic function. What we have to do now, we have to choose the values of y, and we will find the corresponding values of x, somewhat opposite. We will give the values of the dependent variable, and we will find the corresponding values of our independent variable x. Now 10 to the power y is equals to x is an exponential function now. So before going to the graph of the exponential function, we recall that the domain of the exponential function is the set of all reals, and the range is the set of all positive reals. That is, the graph always lie above the x-axis. Okay, now we consider our function in the exponential form. 10 to the power y is equals to x, and the corresponding values of y and the corresponding values of x. When y is 0, we obtain x is 1. When y is 1, we obtain x is 2. When y is 3, when y is 2, we obtain, no, when y is 1, we obtain here as 10. 10 to the power 1, 1. 10 square is 100. 10 cube is 1000. And now some negative values. When y is minus 1, we obtain 1 by 10, which is 0.1. When y is minus 2, we obtain 0.01, and so on. And we sketch the graph of this function. So when x is 1, y is 0. When x is, let's say, 10, y is 1, means this point. For 100, this is 2. Okay. And for negative values, when x is minus 1, this is, when x is 0.1, y is minus 1, that is somewhere here. And when x is 0.01, this is minus 2. And now we connect these points. Passing, oops, it's very fixed. So in short, the graph will look like this, with this point as 1, 0. And what do we observe from this graph of a log function? What can we say about the domain now? The domain is, no matter whatever the values we take, x is only positive allowed. So the domain is the set of all positive reals. Okay, our range in this case is, we have some positive values, some negative values as well. So the range is the whole real line. Do we have any x-intercept? Yes, x-intercept is 1, 0. Do we have any y-intercept? No, the graph continues, but it never touches the y-axis. No. Is it an increasing function? Yes, it is an increasing function, rising from left to right. Okay, when x is greater than 1, the values of y are positive. When x is equals to 1, we have an x-intercept, that is y is 0. And when x is between 0 and 1, the values of y are negative. So this is basically the graph of our logarithmic function with our domain as the set of all positive reals. And in the beginning we have said that logs are nothing but the inverse of exponential functions. We can clearly see from the domain and range that now the domain is the set of all positive reals, which was the range of our exponential function, and here the range is a set of all reals, which was the domain of our exponential functions. There we had only y-intercept 0, 1 and no x-intercept. Here we have x-intercept 1, 0 and no y-intercept. Graph is an increasing function rising from left to right and behaves in both the manners. When x is equals to 1, we have an intercept. For positive values, the graph is above the x-axis. For negative values, the graph is below the x-axis. Okay, now we consider our natural log function. That is when we have y is equals to natural log of x with the same condition that x is strictly greater than 0. Now we can graph this function by using two methods. Either we give the values of x and we obtain the corresponding values of y by using a table or a calculator, or the function can be graphed directly. Okay, if we have the values of x and the y, for example, when x is 0.1, y is negative minus 2.3026. We can use the calculator to find the value of natural log when x is 0.1. When x is 0.5, again we have a negative value minus 0.693. Okay, when we have x is equals to 1, log of 1 is always 0. When we have x is equals to e, log of e should be equals to 1. If we have e square, we should obtain 2 and so on. And now the graph. This is our point 1, 0, our x-intercept. When x is equals to e, the value is 1 for e square, which is approximately equals to 7.089. The value is 2. For decimal values, the graph is below the x-axis. So first we connect these 3 points, and now the graph is below the x-axis. So the graph of natural log behaves exactly in the same way as the graph of log to the base 10. They have the same intercept, they are increasing functions, same domain, same range, and no y-intercept. For decimal values of the domain, the graph is below the x-axis. For x is equals to 1, the graph has the x-intercept. And for x greater than 1, the graph is above the x-axis. Okay, now we consider another function. Or alternatively, I have said that we can graph this function by using two procedures, either by taking the values or alternatively by converting our natural log function into the exponential form, which we have done in our first example. That is when we graph our function of log to the base 10. Okay. If we want to consider another function, y is equals to log of x to the base 1 by 2. If we remember that the condition on x is that x should be strictly greater than 0, the condition on the base is that b should be positive, different from 1. So b is equals to 1 by 2 is allowed, no problem. Now how we will find the graph of this function? We will convert this logarithmic function into the exponential form by writing it as 1 by 2 to the power y is equals to x. Now some values of x and the values of y. When x is 1 or when y is 0, we obtain 1. When y is 1, we obtain 1 by 2. When y is 2, we obtain 1 by 4. And now the negative values. When y is minus 1, we obtain 2. When y is minus 2, we obtain 4. By using these values, we will sketch the graph of our log function with some base less than 1. Okay, this is our x, this is our y, and what do we get when x is 1, y is 0? 1 by 2, we obtain 1. For 1 by 4, we obtain 2. Okay. For 2, we obtain minus 1, that is this point. For 4, we obtain minus 2. And now we have to connect all these points. Connecting these points, we obtain something like this. Or if I draw it again, we obtain some graph like this. So this is the graph of our function log of x to the base 1 by 2. Okay, and now we have to look at some properties or the characteristics of this log function with the help of the graph. What is the domain here? The domain here is only the set of all positive reals. Domain is the set of all positive reals, that is not including 0, this open interval 0 to infinity. Our range is the set of all reals, that is minus infinity to infinity. Now the graph is a decreasing function, falling from left to right. Falling from left to right. We have an x-intercept as 1, 0, and we have no y-intercept. Okay, when x is between 0 and 1, y is positive. When x is equals to 1, y is 0, and when x is greater than 1, y is negative. So we have sketched the graphs of two log functions, and now we will summarize the properties of two cases. Okay, first case was y is equals to log of x to the base b when the base b is greater than 1. That is, first case was when we have considered the graph of log of x to the base 10. And the second case was y is equals to log of x to the base b when the base strictly lies between 0 and 1. That is our case when b is equals to 1 by 2. In this case, we have seen that the graph is always like this, and in this case we have seen that the graph is always like this. That is when b is greater than 1, when b is less than 1. The domain is the common domain. there is no issue. They have some common properties as well. The domain is the set of all positive reals. Range is the set of all reals. They both have x-intercept at 1. Now, the graph of the function when b is greater than 1 is an increasing function rising from left to right, and the graph when b is between 0 and 1 is a decreasing function falling from left to right. And when x is between 0 and 1, y is positive, but here we have the opposite case. When x is between 0 and 1, y is negative. For x equals to 1, both are 0. When x is greater than 1, we have y is negative here. If x is y is positive here. Y is positive when x is greater than 1. Y is negative. Y is negative. So now we have summarized the properties and the characteristics of logarithmic functions, and we can see that for different values of b, the graph are almost the opposite of each other. Now we consider a function y is equals to 5 minus 3 times log of x plus 1, and with the condition that x is strictly greater than minus 1, because if x is equals to minus 1, we will obtain log of 0, and log of 0 is not defined. So here we really have to pay attention that our domain will be the set of all reals strictly greater than minus 1. Okay. We will sketch the graph of this function by putting the values of x and obtaining the corresponding values of y by using the calculator. When x is 0, we obtain log of 1, which is 0, and y is equals to 5. When x is equals to 1, we obtain 2.92. When x is equals to 2, by using the calculator we obtain 1.7. When x is equals to 5, we obtain the negative value minus 0.37. And when x is equals to minus 0.5, we obtain a positive value 7.079. And the graph, if we have this line, when x is 0, y is 5, means this point. When x is 1, it is somewhere here. For 2, it is going more down, and so on. For 5, it is somewhat smaller values. And by connecting these points, what do we obtain? The graph looks like going this way, and this is the point 5. And on the left side is continuing this way, but never crosses this line x is equals to minus 1. So the graph never touches this line x is equals to minus 1. The domain is the set of all reals. Here the domain is a slightly changed, which is the set of all reals strictly greater than minus 1, and the range is the set of all reals. That is the whole real line. So by putting the values of x, we can obtain the corresponding values of y, and we can sketch the graph of our log function. Now we come to some word problems, some applications of log functions. We are given the information that a newly created welfare agency is attempting to determine the number of analysts to hire to process welfare applications. Efficiency experts estimate that the average cost C of processing an application is a function of the number of analysts X. Specifically, the cost function is C function of X, that is the number of analysts, is given as 0.001 X square minus 5 log of X plus 60. So we are given this log function and we are asked to find the average cost per application if 20 analysts are used and if 50 analysts are used, and what will be the graph of this function. So we rewrite our logarithmic function f of x as 0.001 x square minus 5 log of x plus 60, and first thing we are asked to find what will be the cost if 20 analysts are used. Simply put the value of 20 in the as x. We obtain 0.0120 square minus 5 into log of 20 plus 60, which is 0.4 minus 5 into 2.99 plus 60, and by simplifying we obtain equals to 45.42 will be the cost if 20 analysts are used. Similarly, we can find the cost if 50 analysts are used by putting the value of x is equals to 50 in our logarithmic equation or logarithmic function. This should be 50 square minus 5 natural log of 50 plus 60, and simplifying we obtain that the cost will be somewhat reduced to 42.94, and the graph of this function, if this is 20, this is 50, then when x is equals to 1, natural log of 1 will be 0, and we will obtain some value very close to 60. For the case of 20, this is 45. For the case of 50, this is, let's say, 42. So the graph looks like this. So if we are given a logarithmic function, we can easily find the values of the variable by putting the value in the log function, and we will obtain our required cost function. We consider one more application, that an experiment was conducted to determine the effects of elapsed time on a person's memory. Subjects were asked to look at a picture which contained many objects. At different time intervals following this, they would be asked to recall as many objects as they could. Based on experiment, the following function was developed, that is r is equals to function of time, which is equals to 84 minus 25 natural log of t, with the condition that time is greater than equals to 1, where r denotes the average percentage recall and t denotes the time since studying the picture in hours. And we are asked to find the average percentage recall after 1 hour of studying the picture and after 10 hours, and further we have to sketch the function. After 1 hour means f of 1 will be equals to 84 minus 25 into natural log of 1, which is 0, which is 84%. After 10 hours, the percentage remembered, after 10 hours the memory remembered will be 84 minus 25 into natural log of 10, which is 84 minus 25 into 2.302, 2, and simplifying we obtain 26.435%. And the graph will be somewhat like, that is when time is 1, it was, if this is 100, it was 84. When time was 10 hours, it was 26. So the graph is clearly a decreasing function of time. And this is the memory recall. With this we end our today's lecture. Let us summarize what we have studied today. We have studied the definition of logarithms and the equivalent statements of logarithm and the exponential equations. We have also seen the notations of the common logarithm, that is log to the base 10, and natural logarithm, that is log to the base e. Then we have seen some properties of logarithms along with some examples. And with the help of these properties, we have solved the logarithmic equations. Then we have seen the graphs of logarithms with two particular cases, that is when b is greater than 1 and the case when b is strictly between 0 and 1. In the end, we have seen some word problems, that is when we obtain the logarithmic equation from our real world problem. With this we end our today's lecture, and in our next lecture we will see some applications of exponential functions and exponential equations and logarithmic equations. With this we end our today's lecture. See you in the next lecture. Allah Hafiz, students.